The guy who's speaking is, my name is James Scoggins, or JB Scoggins. I'm a research aerospace engineer in the aerodynamics branch at the Langley Research Center. So I'm going to be co-chairing today with William, and I'll let William introduce himself before I hand it off to him. So he'll be doing the last two talks, and I'll chair the first three today. So Sergio, let me go ahead and introduce you, if that's okay. So our first presenter today is Sergio Freire. I hope I'm pronouncing that right. Please correct me if I'm wrong. So he obtained his bachelor's in aerospace engineering from Polytechnic University of Madrid and his master's from the Polytechnic University of Valencia, Spain. In 2018, he joined NASA Ames Advanced Supercomputing Division to work on high-fidelity ArcJet simulations, focusing on radiative heat transfer modeling and meshing algorithms to automate the grid generation process of ArcJet geometries. In 2020, he joined NASA Ames Thermal Protection Materials branch as part of the Entry Systems modeling team. And since then, he has been working on multi-scale solid mechanics modeling of thermal protection system materials to simulate their structural behavior during atmospheric entry, contributing to the development of in-house developed modeling codes. So with that, Sergio, the floor is yours.
Okay, thank you for the introduction, JB, and thank you everyone for attending. My name is Izquierdo. I work at the Thermal Protection Materials branch at NASA Ames Research Center, and I'm going to present an overview of how to compute effective mechanical properties and model the potential mechanical erosion of TPS materials. I'm going to start the presentation with a brief motivation slide of why we're interested in solid mechanics modeling of TPS materials at different scales. And then the presentation is divided into two main sections. The first one explains the methodology to compute the effective mechanical properties by modeling the material at the micro and meso scale with PUMA. And the second part goes over how we can use those mechanical properties together with the new solid mechanics module implemented in PATO to model the potential mechanical erosion on the TPS surface at the macro scale. The last slide will be the conclusions and the proposed future work. So the reason of this effort is that solid mechanics modeling of TPS materials allows us to understand their mechanical performance during atmospheric entry. To do this modeling at full scale, we need the mechanical properties of the material, and this can be obtained through micromechanics modeling of the material's microstructure. In our case, for this modeling process, we are using two in-house developed software packages, the porous microstructure analysis PUMA and the microscale for the microscale modeling, and the porous material analysis toolbox based on OpenFOAM or PATO for the macroscale. These are the two softwares. In this slide, and the next one, I just established an introduction to PUMA. As I said, PUMA is an open source computational framework developed at NASA that allows us to either artificially generate microstructures or import them from microtomography scans, and then compute material properties such as porosity, surface area, effective thermal conductivity, pore diameter, tortuosity, permeability, and so on. It also enables the computation of mechanical properties through its anisotropic elasticity solver. The lead developers of PUMA are Joseph Ferguson and Federico Semeraro, and I include in this slide some information about the installation process, where to find the documentation and tutorials, and the link to the Git repository. I also have to mention that PUMA recently won the 2022 NASA Software of the Year Award. As I said, with PUMA, we focus on multi-scale modeling to obtain the mechanical properties, and specifically there are 3 scale levels or modeling steps for a composite TPS material. The first step is modeling the matrix at the smallest scale, and then we can model the tows or yarns that form the structure of the material. And after getting the results for both of these constituents, we are able to model the unit cell. This multi-scale modeling process allows for TPS optimization by, for example, changing the resin infusion process, the constituent selection, the tows structure, and so on. I'm not going to go into detail, but PUMA's elasticity solver is a finite volume voxel-based stress analysis solver for anisotropic linear elastic materials. And the discretization is self-centered, and the phase stress values are approximated using the multi-point stress approximation method. Using this solver, the effective mechanical properties at the macro scale can be computed following the representative volume element homogenization method, which consists on running a simulation for each principal direction, so 3 in total, imposing a known displacement on each phase while keeping the opposite phase fixed. And then we apply symmetry or periodic boundary conditions to the other 4 phases. After that, we can solve the stress field generated in the material and obtain the anisotropic elasticity tensor C. Then, assuming that the material is isotropic or orthotropic, it is possible to obtain the effective jam modulus E and Poisson ratio from the C tensor. A similar approach can be used for the pure shear cases to obtain the shear modulus. So, following the procedure explained in the previous slide, this slide and the next two are a quick summary of the multi-scale modeling process for a 3D woven TPS material. The left part of the slide shows what a porous matrix looks like in real life on the top, and different domains with different porosities and pore sizes generated with PUMA to model the microstructure of porous resin. And the results for the porous matrix can be validated with some empirical questions, for example, the one from Baird and Roberts. On the center, we can observe the modeling of TFAWS with different packing ratios or volume ratio of fibers versus phenolic resin. And there are also some equations we can use to validate some of the mechanical properties of the TFAWS, specifically can use the rule of mixtures and the Halpin-Tsai, Nielsen, and Chamis equations. And on the right, we can observe the representation of the unit cell that we are trying to model. Here we can observe the results of the simulations. Oops, sorry. The images on top correspond to the displacement imposed in one direction, and the images on the bottom are the stress field as a result of this displacement for the porous matrix on the left and for the TFAWS on the right. The two plots on the left represent the jam modulus of the matrix as a function of porosity and the diameter of the spherical pores in voxels, and how it compares with the analytical equations used for validation. And we can observe that there is a great agreement with Roberts' equation, and Baird's equation is not that far off. The plots on the right represent the jam moduli and the Poisson ratios in the longitudinal and transverse directions for the different fair volume fractions and matrix porosities. And we can observe also how they compare against the validation expressions. I don't want to spend too much time here, but we can observe how, for example, for the transverse direction, higher volume fraction and lower matrix porosities lead to higher jam modulus. And how the PUMA results, which are the dots in this plot, fall in between the approximations from Halpin-Tsai, Nielsen, and Chamis. The same methodology used at the microscale for the constituents was applied to obtain the effective mechanical properties of the unit cell. Again, on the top, we can observe the displacement fields, and on the bottom, the stress distribution in X, Y, and Z directions under different normal load conditions applied to obtain the mechanical properties. In these images, the matrix phase is hidden just for visualization purposes. On the right, we can observe the graphs with the results with the jam modulus in the 3 principal directions on the top and the Poisson ratios on the bottom, and how all these values are affected by the different matrix porosities and fair volume fractions of the TFAWS. So these are some of the mechanical properties we need for full-scale modeling with PATO. This introduction to PATO is the beginning of the second part of the presentation. PATO is an open source software for computational material response of reactive porous materials submitted to high enthalpy environments. It enables modeling most of the entry material response physics like equilibrium chemistry, phenolic chemistry, ablation, paralysis, heat conduction, and so on. Some of the recent developments in the code are the coupling with CFD, the Picano modeling, a unified solver and the mechanical erosion modeling. As I said before, the mechanical erosion model relies on mechanical erosion on the mechanical properties computed with Puma. The point of contact for Pato is Jamie Maurice, and I include in this slide some information about the official website, the installation process, where to find documentation and tutorials, and also links to the Git repositories. The goal of the full-scale modeling with Pato is to predict the mechanical response of TPS materials, and specifically to determine if there is additional surface recession in the TPS surface as a result of mechanical erosion due to different loads experienced during atmospheric entry. And these loads might be, for example, the external forces on the heat shield surface, like the shear stress and the pressure from the flow field, thermal stresses induced by the material's temperature field, normal stress induced by the pyrolysis gas buildup, and also shrinkage due to pyrolysis of the material itself. So the same physics also apply to intermescent gap filler materials such as RTB, which are important to understand to model the differential recession between TPS material and the gap filler. And this part of the presentation is an overview of the mechanical erosion model implemented in Pato that accounts for this potential additional mass removal, specifically during high shear conditions. This slide is a flow diagram that shows how the mechanical erosion model was implemented. Having the results from Dippler, the thermal environment is extracted with B-layer, and the surface and the wall shear stress tensor is obtained from the post-flow utility. Then Pato's material response solver computes the pressure and the temperature field inside the material as well as the surface recession. And the next step is updating the mechanical properties of the material as a function of temperature, accounting for the local orientation of the material itself. And then the stress analysis solver computes the stress field and the displacement using the CFD results as boundary condition. The failure criteria and the mass removal models define the regions on the surface where the stress is higher than 13 threshold, and then move the mesh accordingly to remove this material. And the outcome of this is the total recession of the material, which also accounts for the mass loss due to the mechanical erosion. As a quick overview of the stress analysis solver, assuming small strains and small rotations, the stress and displacements are obtained by solving this equation, which is the conservation of linear momentum. To solve it in Pato with OpenFOAM, we use a segregated solution approach that allows to solve the Goldman equation independently for each direction, and then additional iterations are performed until the explicit terms change less than some predefined tolerance. And at this point, the implicit term and the second explicit term cancel each other, and the calculated displacement field satisfies the Goldman equation. This solver works for isotropic and orthotropic material, following the constitutive laws shown here, and for the orthotropic case, it needs 9 independent material parameters, which are the orthotropic mechanical properties, and we can obtain with Puma, for example. This is a 3D validation case for the orthotropic stress analysis solver that includes thermal stresses. The model is just a cube-shaped structural maze made of 125,000 elements with the boundary conditions of zero displacement applied on all the boundaries, so the volume remains constant. And also the temperature of the body was increased by 200 Kelvin with respect to our reference temperature. And we applied a body acceleration of 9,800 meters per second squared in the x direction. So we also have some mechanical load in addition to the thermal stress. The mechanical properties used are the ones shown here for the thermal expansion coefficient, Poisson ratios, the jump moduli, and the shear moduli in the different directions. To validate the solver, the results were compared against the solution from ANSYS. And on the right, we can observe here how there is a very good agreement between the simulation from Pato and the simulation from ANSYS for the stress in the x direction, and there is a maximum error of just 0.005%. This slide, we can observe the normal stress for directions y and z, and the shear stress for the y-z direction. And the maximum error for all cases also is very small, but due to using different visualization softwares and differences in the color map labeling, some errors might look a little bit higher in the images than what they really are. Then following with our model, the failure criteria allows us to find the regions where mechanical erosion might happen. The model used follows the maximum stress failure theory, in which the maximum stresses of each mode or direction are compared against the material's strength, following this equation for the 2D case, where FTU and FCU are the ultimate tension and compression strengths in the X and Y direction, and FSU is the ultimate shear strength. For sigma is the stress tensor computed by the stress analysis solver. An example of how this failure criteria is applied can be observed in the figure below. Regarding the mass removal model, it follows the two equations shown here. The first one is the surface recession rate, which is the failing distance computed with a mesh search algorithm divided by a time step. And the second one is the mass loss, which also takes into account the solid density and the surface area. The failing region is removed only if its topology is connected to the surface, and if a region fails, the mesh is moved to adapt it to the remaining material. So to conclude, we described a methodology to carry out multi-scale analysis of TPS composites with PUMA to obtain the homogenized orthotropic mechanical properties. Firstly, we model the constituents at the microscale, and then we use the results to model the unit cell. And the results were validated for the porous matrix and the JAS of a 3D point TPS composite by comparing them to some empirical equations listed in the literature. And the second part, we described the mechanical erosion model implemented in PATO to predict the mechanical response to TPS materials during the atmospheric entry. And this model relies on having accurate TPS mechanical properties, which can be computed with PUMA. And the implemented stress analysis solver was validated against results from ANSYS. And we also saw the implemented failure criteria mass removal model to account for the potential mechanical erosion. And as a future work, we would like to validate the full-scale mechanical erosion model coupled with the rest of the entry physics against results obtained from other experiments. And these are some of the references that we use in the presentation. Thank you, everyone. If you have any questions, I'll be happy to answer them.
I was just curious, do you, for this shear stress failure model, is there a plan or attempt to try and validate that through like ArcJet experiments with some kind of shear testing, or are you aware of anything?
Our plan is to validate this, and I know there were some shear tests that were already performed, so we'll try to gather that data and we'll see if we need to propose like specific tests to validate the full model. Yeah, what I just showed here was like the validation, but kind of like the solver itself, like just as a solver. And we also run, I don't have it here, but we run also just a test case to make sure the failure criteria and the mass removal model were working as expected, just by having dummy mechanical properties, and dummy limits, just to make sure the solver was doing what it was supposed to do. So we did that and also worked, but we haven't run yet like a full model of which we have, data we can compare against.
Right. Yeah. So still in the kind of verification stage.